In this video, we're going to expand upon our knowledge of LeChatelier's principle and look at a way to quantitatively predict which way the equilibrium is going to shift. So the first thing that we can do, because we're dealing with KEQ calculations, is just to write out what our KEQ expression is going to be. I'm going to assume that you can do that rather fluently at this point. Next, let's correct the problem with our quantities, where all of them are given in moles, by dividing the number of moles of each gas by the volume of the container in order to find the concentration. 2 divided by 2 is 1 mole per liter of nitrogen monoxide. 0.2 divided by 2 is 0.10 moles per liter of oxygen gas. And 0.4 divided by 2 is 0.20 moles per liter of nitrogen dioxide. Now, if we were to look at these numbers and consider what the question is asking, is the reaction at equilibrium? If you look at these numbers completely in isolation, there's only one answer that you can come up with: is this reaction at equilibrium? So if you want a more intelligent answer than who knows, we actually need to take these numbers here and put them into the expression for KEQ and then compare the number that we get with the actual measurement for KEQ that we're given, which happens to be 49 in this case. Now, normally what we would be doing if we put quantities into the formula for KEQ is calculating the magnitude of KEQ itself. But since we're given that, we're not calculating KEQ in this case, which means that we need a different variable to indicate that we don't know whether this reaction is at equilibrium. So we use the variable Q, which is what we call the reaction quotient. And again, solving for the reaction quotient is done exactly the same way as calculating KEQ, by simply inputting our concentrations in to the corresponding part of our KEQ expression. So that's exactly what I'm going to do now. So concentration of nitrogen dioxide that we were given is 0.2 squared. Concentration of nitrogen monoxide is 1.0 squared times the concentration of oxygen gas, 0.1. So we can technically solve this without a calculator. 0.2 times 0.2 is 0.040 with significant digits. 1 to any exponent is just going to be 1, so I'm not going to bother writing that in. And when we divide anything by 0.1, that's the same thing as dividing by 1 over 10, which is the same thing as multiplying by 10, which means that our Q value is 0.40. Now, in terms of the meaning of this, it helps to remember what KEQ actually represents. We'll get to that in a second. Now, once we calculate Q, there are 3 different possibilities of what Q can be relative to KEQ. Q can be less than KEQ, as it is in this case, because 0.40 is significantly less than 49. Q can be equal to KEQ, or Q can be greater than KEQ. And the significance of this in terms of predicting an equilibrium shift all have to do with what KEQ represents, which is simply a ratio of the concentration of products compared to the concentration of reactants. Now, just to explicitly compare the two, our Q value is 0.40 and the KEQ value is let's ignore that mistake there, 49. So we can clearly see that Q is less than the value of KEQ. Now, what this means in terms of equilibrium shifts, we can actually see by looking at what KEQ represents. In order for Q to be less than KEQ, this could be true for 2 different reasons. Number 1, we have far fewer products than exist at equilibrium, because decreasing the numerator will decrease the value of Q, or we have far too many reactants, which would also decrease the value of Q compared to KEQ, but the result of this is the same. If we have too many reactants or not enough products, that would mean that the forward rate is greater than the reverse rate is, which means that our equilibrium is going to shift in favor of the products. And that's exactly what would happen here. So in this case, regardless of whether we have not enough products or too many reactants, because of this situation, that would mean that our equilibrium is going to shift in favor of the products because the forward rate is greater than the reverse rate. So as a consequence, our quantity or our concentration of nitrogen dioxide will increase while the concentration of oxygen and nitrogen monoxide will decrease. And if that happens, the value of Q will increase until the value of Q becomes equal to KEQ. And if this is the case, nothing should happen because we are at equilibrium. Now, it's not true in this case, but analyzing how an equilibrium shift would occur if Q is greater than KEQ is fairly intuitive as well. So again, if we consider what KEQ represents, concentration of products compared to concentration of reactants, in order to make Q greater than KEQ, we can either do that by having a much higher concentration of products compared to the equilibrium situation, or too few reactants. And in either case, that means that the opposite is going to be true. It means that our reverse rate is now greater than the forward rate because either we have too many products, which will speed up the reverse reaction, or too few reactants, which will slow down the forward reaction, and the result of which is that we will get an equilibrium shift in favor of the reactants. In the next video, we're going to look at the same situation, predicting an equilibrium shift by comparing the concentration of products and reactants in a situation with the equilibrium situation, only we're going to be expanding on that and actually calculating what the concentration of reactants and products are going to be when the new equilibrium is formed.